Welcome back, Focus Learners. Let's get right into it. Today, we're exploring a seriously fascinating role in the environmental science world. We're demystifying the FAEWP. That's the Functional Area Expert for Water Pollution. When a new industrial project gets proposed, these are the folks on the ground. They're the architects, the environmental detectives of the whole EIA process. And their work? It literally shields our water systems from irreversible damage. Quickly, here's our roadmap for this explainer. We're going to cover the water pollution expert, reconnaissance and source inventory, surface and groundwater monitoring, water balance and wastewater, impact prediction and mitigation, and finally, QMS and quality assurance. Let's roll. Okay, let's dive right into this. A functional area expert for water pollution isn't just someone walking around collecting water in a jar, right? They're highly specialized professionals. They're tasked with designing those complex sampling networks, characterizing effluent streams, and, crucially, actively predicting exactly how a future project might impact local water bodies. Basically, they translate raw baseline data into actionable, legal pollution prevention strategies. Section 1. The Water Pollution Expert. So who exactly gets to do this kind of critical work? Well, it takes a tremendous amount of rigorous education and hands-on experience, as you might guess. To even be considered, these experts need specific degrees in engineering, like environmental, chemical, or civil, or hardcore sciences like hydrology or toxicology. And once they're qualified, the duties are intense. They're designing the entire water and wastewater sampling network. They're out there performing water use auditing, figuring out if a facility can actually pull off zero liquid discharge, meaning absolutely no wastewater leaves the plant boundaries. No way around it, they have to use advanced water quality modeling to predict downstream impacts before a single brick is even laid. Moving on to Section 2, Reconnaissance and Source Inventory. This is the very first step of the project lifecycle. I want you to step into the phase shoes for just a second. You arrive at the site. Before you set up a single piece of lab equipment, what is the environment already telling you? You really have to look for physical clues. What are the natural drainage patterns? What's the historical flood level like? Is there any evidence of waterlogging? You are essentially observing the ecosystem's baseline behavior right off the bat. Now, what's really interesting here is that reconnaissance is not just about the specific project footprint. It's about understanding the whole surrounding community. The expert actually has to audit the water profile of every single village within a 5-kilometer buffer. They're mapping existing industries within a 10-kilometer buffer and categorizing them by pollution risk. They check existing groundwater tables both pre- and post-monsoon and even locate nearby sewage treatment plants just to see if they're legally compliant. You are building a massive, comprehensive neighborhood profile. And man, do they document this with incredible precision. Using structured forms like the QFAM035 datasheet, the FAE meticulously logs every single hand pump, drain, borewell, and canal. We're talking exact GPS coordinates, direction from the site, distance, and really critical remarks like the depth of a well, or whether the water is used for drinking versus just irrigation. This is what establishes a totally bulletproof water source inventory. Section 3, Surface and Groundwater Monitoring. Once the visual reconnaissance is done, we transition to the rigorous baseline data collection. And there's a really crucial distinction here in how we monitor different types of water. For surface water, rivers, streams, monitoring requires tracking upstream to catch the water before it hits the site and downstream to see the potential impact zone. But groundwater, that doesn't work like a visible river. For groundwater, experts have to understand subsurface aquifer flows. They're measuring upgradient and downgradient to capture an accurate baseline right beneath the earth. Now, collecting all this data involves a strict physical chain of custody. Why? Because it needs to be absolutely irrefutable. No room for legal loopholes later on. So first, monitoring locations are set based on that initial site reconnaissance we talked about. Second, samples have to be collected across different seasons to capture both pre-monsoon dry periods and post-monsoon recharges. Third, those samples are chemically preserved and securely transported. And finally, the actual analysis, that can only happen at an NABL-accredited or Ministry of Environment recognized laboratory. Strict rules for sure. I really want to highlight this number, 500. This represents the maximum acceptable limit of total dissolved solids, TDS, in milligrams per liter for drinking water, according to the standard IS 10500. Think about it. This is the water that you and your community might actually end up drinking. It makes this standard absolutely critical for public health. And honestly, it's just one of dozens of metrics, from biochemical oxygen demand to heavy metals like lead and arsenic, that the FAE is closely watching. Section 4, Water Balance and Wastewater. With our baseline data secured, we look at how the expert balances massive water demands against conservation. Let's unpack the core concept of water budgeting. The expert calculates the total water demand, so that's adding up domestic use, industrial processing, cooling towers, greenbelt maintenance, the whole shebang. But they don't just stop there. They actively look for zero liquid discharge strategies to maximize water recycling and reuse. And this brilliantly illustrates how, by subtracting that recycled water from the total demand, the expert finds the critical net fresh water requirement. It ensures the project takes absolutely no more from the environment than it needs to. All right, Section 5, Impact, Prediction, and Mitigation. All that data collected so far, it's about to be turned into a concrete environmental management plan, or EMP. This is where the FAE suggests specific engineered control measures to actually neutralize predicted impacts. We're talking about designing sewage treatment plants to push biochemical oxygen demand below 10 milligrams per liter. We're talking tailoring effluent treatment plants to hit strict state pollution board consents. They're installing oil and grease traps in workshops, mandating rainwater harvesting structures based on groundwater board norms, and making sure collection tanks are fully lined to prevent any kind of toxic seepage into the groundwater below. And here, as you'll see, the expert literally models the future. They take the baseline quality, let's say a groundwater level sitting at 10 meters below ground level. Then they model the project's impact, predicting maybe a drawdown of 2 meters. That gives us a final predicted quality of 12 meters below ground level. Now, the absolutely vital step here is ensuring that this final predicted number still falls safely within compliant legal standards, because if it doesn't, the whole project design has to be changed. Simple as that. Section 6, QMS and Quality Assurance. Because managing all this complex, highly sensitive data requires a serious organizational framework. Which brings us right to Appendix B of the standard scheme. This establishes a rigid quality management system, or QMS. Think of it like this. All the moving parts we've just discussed, the complex sampling networks, the lab transports, the impact modeling, they're all held together by this ISO 9001-inspired framework. I love this quote from the scheme documents because it captures the entire philosophy. Creates a culture of doing things right the very first time. And why is this so crucial? Well, in environmental science, once a factory is built and operating, you can't exactly go back in time to collect pre-project baseline data, right? Getting it right the first time isn't just a nice goal. It is legally and scientifically mandatory. Let's move to and see how this builds into a highly practical 3-tier QMS documentation system. Tier 1, that's your high-level quality manual. Tier 2 contained the documented procedures, detailing exactly how to select those sampling locations or handle lab workflows. Then Tier 3 brings it right down to the ground level with specific work instructions and checklists, like that QFM 035 datasheet we looked at earlier. It totally eliminates guesswork and ensures complete accountability for the FAE's job. So the crucial point here is that the FAEWP isn't just passively monitoring pollution. They are actively designing systems to prevent it before it ever happens. Which leaves us with a pretty powerful thought. If our baseline data and modeling can accurately predict the exact environmental footprint of tomorrow's industries, just how close are we to achieving universal zero liquid discharge across all industrial sectors? Think about it. Thank you so much for engaging with this explainer, focus learners. Keep asking those big questions, and I highly encourage you to look deeper into the fascinating world of environmental auditing and the incredible people who protect our water.